Hello class, in this video I am going to talk about the graphical solution of linear problems with two variables. I will explain it with a simple example, and by following the similar steps you can solve more complex problems. So let's first focus on the example. Imagine a factory mainly producing two products. A worker in this factory can make 2 of product number 1 and 3 of the product number 2 per hour. And also there is a limitation for the packing machine. The packing machine can only pack 4 of these products per hour. And the profit of the first item is $15, and the profit of the second item is $10. And I mean that by selling each item of the product number 1, we can get $15, and by selling each item of product number 2, we can get $10. And the question is, how much of these products should we produce to maximize the profit of the factory? Very simple problem. First, we define the decision variables as x1 and x2. x1 is the number of product number 1 manufactured in each hour, and x2 is the number of product number 2 manufactured in each hour. Based on this, I have the objective function as 15x1 plus 10x2, which is built based on the profit of the products. Then I have the constraint of the capacity for product number 1, the capacity of product number 2, the capacity of production, I mean. And this is the packing machine limitation. And then both of the x's should be greater than or equal to 0. So very simple. To start the graphical solution, we should first start plotting each of the constraints on the coordinates and try to define their related affecting areas. So draw each constraint on the coordinate axis. Graph each constraint one by one by pretending that they are equalities. I mean that pretend that all of the less than or equal symbols are equalities. Also, all of the greater than and greater than or equal signs are just equalities. And then plot the line. As each line is created, divide the region into 3 parts with respect to each line. So I have the on the line, I have above the line, and I have below the line. For this case, for example, I have the region C, the below line. I have just named it C, and the related inequality is A1x1 plus A2x2 less than or equal to B1. And to identify the feasible region for this particular constraint, pick a point in either side of the line and plug its coordinates into the constraints. If it satisfies the condition, this side is feasible. Otherwise, the other side is feasible. And for equality constraints, only the points on the lines are feasible. Here, let's focus on the constraint number 2. All right. Just let's pick up, for example, 4. Does it satisfy our inequality? Is 4 less than 2? No. So let's try another point, x1 equal to 1. And in this case, we see that the value just satisfies our constraint, satisfies our condition. And well, based on this, we obtain the related affected area but by this constraint with this particular constraint. Very simple. And the second constraint is x2 less than or equal to 3. Following the same logic, we obtain the related cross-hatched area, as you can see. For example, where is the location of x2 equal to 1? Is it below the line or above the line? You see, by defining some sample points, you can get the related area simply. For the third constraint, again, first change the inequality to equality and plot the line. In this case, we have x1 plus x2 equal to 4. You can try some points such as point 0, 0 or 1 and 1 and see in what side of the line they are located. By doing so, we get the cross-hatched area, as you can see. Just a reminder that the variables are non-negative, so we are talking about only the positive quadrant of the coordinates. And after defining all the affected areas by the constraints, we get the feasible region as the intersection of all the constraints, as you can see. You can see this is the direction of each constraint, and then we will find the intersection of these 5 directions, where the 2 of them are non-negativity directions. So this is my feasible region. This is the area where my optimal solution will be. We can find the trial isovalue line. It's a line in which all points have the same objective function value. Then we find the optimal isovalue line, which is a parallel line with the trial isovalue line, which passes through the optimal solution. Now we will go into the details. If the problem is of maximizing type, we will move the trial isovalue line in the direction of the objective function vector until we reach to a point that if we pass this point, we will get out of the feasible region. And if the problem is of minimizing type, draw a trial isovalue line and start moving it in the opposite direction of the objective function vector until you reach to the point that the moving more than this will violate the feasible region. So in general, if the feasible region is within the first quadrant of the coordinate system, then for the maximization problem, you are moving the isovalue line objective function parallel to itself far away from the original point 0, 0, while having at least a common point with the feasible region. However, for the minimization problems, the opposite is true. That is, you're moving the isovalue objective function parallel to itself closer to the original point, while having at least a common point with the feasible region. So the question is how we obtain the trial isovalue line. Again, very simple. Draw the objective function vector on the graph, find the perpendicular line of it. It's your isovalue line. Alternatively, by changing the coefficients of x1 and x2 in the objective function, you can get the isovalue lines. I mean, plot the coefficient of the horizontal variable on the vertical axis, and then plot the coefficient of the vertical variable on a horizontal axis. And one more time, just I'm going to repeating again, plot the isovalue lines if the problem is maximizing move in the direction of the objective function vector. It is like sliding a ruler across the graph, like along the isovalue lines. So just imagine one of the isovalue lines as a ruler and start moving it in the correct direction. And where the objective is to maximize, you must slide the ruler up to the point within the feasible region, which is furthest away from the origin. On the other hand, where the objective is to minimize, you must slide the ruler up to the point within the feasible region that is nearest to the origin. So this is my feasible region. This is my objective function. And this is one of my trial isovalue lines. Because the problem is of maximizing type, I will start moving it in the direction of this vector. I will move it. This is one of the trial isovalue lines. Move it until I can't move it, because I will get out of the feasible region. So I will have the optimal isovalue line as the last line that you can see, and also the optimum point as the intersection of this optimal isovalue line with the feasible region. You see, it was very simple. Just follow the steps that I have mentioned and you will have no problems. So how am I going to solve this? So the optimal point is the intersection of two of the equalities. One of them is x1 plus x2 equal to 4, and the other one is x1 equal to 2. Just solve this, because x1 is 2. I can replace it in the second equality, and I will have x2 equal to 2 as well. So the optimum point is 2 and 2. x1 equal to 2 and x2 equals to 2. And again, by replacing this in the objective function, I will get the optimal value of the whole model, which is 50. So one more thing I would like to mention is that there is an alternative method to this isovalue objective function approach with problems that have few constraints and a bounded feasible region. First, find all the corner points, which are called extreme points as well. And the corner points are the vertices of the feasible region. So all the vertices of that feasible region. Once you have the graph of the system of the linear inequalities, then you can look at the graph and easily tell where the corner points are. Okay, just look at the graph. So a corner point is a vertex of the feasible region. But remember, just this is something important, that not every intersection of lines is a corner point. The corner points only occur at vertex of the feasible region. So the feasible region, all the corners of a feasible region. Just repeating again to emphasize this issue. So the vertex of the feasible region. If there is going to be an optimal solution to a linear programming problem, it will occur at one of or more corner points. So this optimal solution is definitely on one of these corner points. Therefore, we can evaluate the objective function at the extreme points to find the optimal value and the optimal solution. And since the objective function is to maximize from the above table, as you can see, we read off all the optimum values to be 50, which is obtainable if two of each products are manufactured per hour, and this at this small factory. I mean that the optimal strategy is to produce two of the product number 1 and two of the product number 2. Again, let's focus on the table one more time. I have the corner point 0, A, B, C, D as the vertices of the feasible region. And I have the related coordinates of them, 0, 0, 2, 0, and so far. And I have the objective function value of each corner point, which is obtained by replacing them in the objective function. So 2, 0, it equals to 30. 2, 2, it equals to 50. And this is the maximum of whole the objective function regarding the corner points. So this is my optimal value. That's it, guys. I hope that you have enjoyed this video. Please let me know if you have any concerns.